The periodic table, as it's normally laid out, really is a fantastic cheat sheet. There's so much information packed into this thing. We can look at chemical properties, bonding, states of matter, and one of the things that we usually want to know is the ground state electron configuration. Because as much as the nucleus plays a role in how the chemical is going to behave, chemistry really involves the outermost electron shell, or the valence electrons, and how those interact with the other electrons and other nuclei. Okay, to make it a bit easier on ourselves to find the ground state electron configuration for each element, first we're going to move around a few things. So let's move helium over beside hydrogen, and that puts it in line with the other elements whose outermost electrons are in the s block. Next, we're going to expand the space between these s orbital elements and the d block to make room for the f block elements. Now that we have the table laid out this way, it's a little easier to see which elements have which orbitals as their outermost electrons. So first we have this blue column, the s block, or the ones that have the outermost electrons in the s orbitals. Then we can move over to the p orbital block, then the d block, and finally lowest down the f block. And we can also number the rows accordingly. So s orbitals start at principal quantum number 1, so we start counting at 1, 2, 3, 4, 5, 6, 7. And we can do the same thing for the p orbitals. So they start at principal quantum number 2, so we go 2, 3, 4, 5, 6, 7. The d block begins at n equals 3, so we go 3, 4, 5, 6. And f starts at 4, so we only have 4 and 5. Okay, so now there's really nothing left to do but count. Okay, for an example, why don't we target gold way down here in the 6th row, because we're going to catch most of the things that we would want to look at on the way, and we get a nice little twist at the end just to restate some facts. Okay, so we start up at hydrogen. So this is 1s, and what we're going to do is count from hydrogen all the way up to 79 gold, filling in every shell as we go. So the 1s orbital is where we begin with hydrogen, and helium is going to complete the 1s shell as 1s2, 2 electrons in the 1s shell. And that's it for the first row. On the second row, the first one we run into is lithium. And so that's going to fill the 2s shell with 2 electrons. And then on the second row, we run into the 2p orbitals. And there are 1, 2, 3, 4, 5, 6 electrons in that. So we write it as 2p6. 6 electrons in the 2p orbital. The next that we'll run into is the 3s, which also has 2 electrons, and then the 3p orbital, which has 6. And now we have a choice between moving to the 3d orbital with its 10 electrons, or the 4s orbital with its 2. So the third shell is going to be closer to the nucleus and have a lower energy, but there are advantages as well to having a complete shell. And the 4s takes that advantage to begin with. And that's one of the advantages of laying the periodic table out as we have, is that the only thing we need to do is run into the very next element, and we can see where its electrons are, and we fill it in as suggested. So we have the next one that we're going to run into is the 4s electrons at potassium. So 4s2. Now we pick up 3d10 and 4p6. Next we'll move on to 5s2 and 4d10 and 5p6. Okay, and here we enter the 6th row, which is where we're going to find gold. And there's a couple of choices here as well, maybe less obvious though. So the first thing that we could do is just run it naively as we have been. So we start at cesium and we say 6s2. Now we pick up the F block, or the F orbital, and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 atoms in that, so that means we're going to have 14 electrons in the F orbital. So we have, and we start at number 4, so that's 4F14. And now we reach the 5D block that contains gold, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9 electrons to get up to gold. So we can write it out as 5D9. The only trouble with writing it out this way, and it's close, but it's not quite fitting with physics. So if we do this experimentally, we find that we don't have a partial D shell. What we do have is a partial 6s shell. Because that is the larger number, and there is such an energetic advantage to closing that fifth level D subshell, what we actually end up with is, instead of 6s2, 4f14, 5d9, we get 6s1, 4f14, 5d10. So we're actually going to complete all the electrons in that 5d subshell, completing the D shell, and pull one of those electrons from the further out, because it is a larger principal quantum number, 6th shell, and leave only one in that 6s block. Okay, so that would be the new and corrected full electron configuration for gold. Fortunately, there is a shorter way of writing this, and for that, all we need to do is identify the closest noble gas that precedes our target atom. So in our case, for gold, we're going to look one row up all the way on the right-hand side, and that is xenon. So we can write this to say it's exactly isoelectronic to xenon all the way up to the 54th electron. So we can write this as xenon to say the electron configuration is exactly the same as xenon, plus 6s1, 4f14, 5d10. And so now this is the electronic configuration for gold in its short form.